Welcome back to Teaching the Unteachables, where we dive into teaching and learning methodologies for professionals like you. This episode is part of episode 74 of Did You Know? The ESCO HVAC Show. Learn more about Regal Rexnord at regalrexnord.com. All right, everyone. Thank you so much for joining us once again on Did You Know? The ESCO HVAC Show. Now, we have done 3 different episodes, Chris, on talking about ECM motors. Isn't that crazy?
Can't believe it.
I know. We're 4 months in right now.
Right.
So we've covered ECM constant torque. We've covered ECM constant airflow. We've covered ECM condenser motors. And so what we're going to wrap up today is kind of going like a high-level view, demystifying ECM motors in general, and bringing in the ECMs really into the classroom. I've also put together a fun little video we're going to share that I want to get your input on and find some potentially incorrect words. So I want you to pay real close attention to it. They're close, but there's better ways to explain it. So,
I'm afraid.
Oh boy, it's gonna be a lot of fun.
I'm rolling up the sleeves. Let's
Roll
go.
up the sleeves. Here we go. And everyone, as always, we truly enjoy you hanging out with us, spending your time talking about a changing industry. What do you think, Chris? Want to bring some clear definition to what ECMs really are?
Let's have some fun.
I like it.
As I was talking to you before the show about when I come out and do classes, technicians don't have a lot of time out of the field. You're always teaching the nuts and bolts, the need to know, get out the door.
Yeah.
And we rarely get a chance to talk about the high level information. And, we use the wrong terminology. We don't really understand where this motor fits in, where that motor fits. Why are there 2 ECMs that seem to do the same thing, but they really don't, and all that kind of stuff. And we've talked about them in the different shows. I can't believe we're on the 4th show already. It's been too much fun. It's like when you go to your, it's like you're headed to that ski trip and all of a sudden you're driving home. You're like, wait, what happened?
Wait, where'd it go?
So yeah, this is going to be a lot of fun. I don't get to teach all this information all the time. Some of it's going to seem a little rudimentary. I am going to start out with some basics just to make sure we're on the same page.
Sure.
The terms of motors in the HVAC industry get confused and convoluted depending on where you learned them. In the southern regions and the northern regions, if you're a heat pump tech or a gas tech, you may think of motors as evaporator and condenser or indoor outdoor. So I like the terms indoor blower motor and outdoor fan motor. And when I start a lot of classes, I start here and say, just to make sure we're on the same page, an indoor blower motor doesn't mean it's indoors, doesn't mean the motor's inside the house. It means that's the air that it moves. It moves the indoor air from the home to the appliance and back to the home. Mm-hmm. And it could be in a gas furnace, an air handler, or a package unit, which means that the indoor blower motor could be inside the structure or it could be outside the structure.
True.
So, yeah. So I just like to, bring those terms in so that we're all on the same page. Again, outdoor fan motor, obviously it's the fan that moves the air across the condensing unit, or evaporator coil if we're in the heating mode of a heat pump. So that could be a split system or package system as well. And if you've ever worked on like a through-the-wall unit or a PTAC for a hotel, that outdoor fan motor could be inside the structure. So
True.
just a little clarity in terms. I don't know, you and I are both nerds of reading schematics and manuals, and if you've read more than one OEM manuals, you've seen more than 10 acronyms used to describe these motors, and it's always fun trying to figure out what those 3 letters, what are they trying to imply by IDM or whatever they've used. So
induced draft, and how does induced draft in the blower?
Exactly. So we're going to talk about HVAC direct drive fractional horsepower motors, and again, sometimes when you're teaching the nuts and bolts, you don't teach these terms. What does direct drive mean? What does fractional FHP mean? Fractional horsepower simply means that these motors are rated in fractions. Don't ask me why it includes 1 horse. I guess 1/1 is a fraction.
I wonder about
But
I didn't think about it till you mentioned it. And I was like,
fractional horsepower motors includes everything 1 horsepower and below. And then direct drive simply implies the type of drive it is. So whatever blade it's running, whether it's a fan blade, axial fan blade, or forward curve fan blade, that is going to be attached directly to the shaft of the motor. There's going to be no
sprocket,
coupling or a shiv
Mm.
in between the motor and what it's actually driving. It's going to be connected directly to that. So just clearing up some terms. And then, the chart shows the typical horsepower ratings you're going to find on the indoor blower and the outdoor fan. This is kind of interesting because if you go back, depending on how old you are, and I'm old, back when air conditioning when it was in its infancy and gas furnaces had been around for a while, you saw quarter, fifth, and third horsepower motors in gas-only systems where you didn't have to move the higher amount of air that's typically required for air conditioning, unless you got 150,000 BTU furnace. Then, of course, you're going to need a larger motor. But today, and when I say today, my career spans 30, we'll just say 30 years. You don't see too many quarter and fifth horsepower motors anymore in the indoor blower category. It's pretty much all third through one. And since the invention of ECM, which is over 30 years as well,
crazy.
You see a lot more half and three-quarter horsepower motors than you do one and third because they're programmable, right? So I can take a motor of a higher horsepower and I can make it act like a motor of a lower horsepower by programming. And I can take a three-quarter horsepower motor, and depending on whether I need 350, 400, or 450 CFM per ton, I can probably get 5 ton of airflow out of a three-quarter horsepower ECM motor. So a little changing industry when ECMs were introduced. And then in the outdoor fan motor market, the opposite shift has happened. It was very common 20 years ago to see third quarter, fifth horsepower motors. And now, especially in your 2.5, 2 ton and 1.5 systems, you're seeing the 6th, the 8th, the 10th. I even saw a 12th horsepower PSC motor the other day. Darn thing wasn't more. I mean, it was like an inch thick. It looked like a ceiling fan motor. Yeah. So it was interesting looking. So yeah, there's some of the ways the industry has changed and some of the terms that we use. So there are basically 4 types of motor technologies used in fractional horsepower HVAC, and those include permanent split capacitor, which the acronym is PSC. We will talk a little bit more about that. You've got constant torque ECM, and then constant airflow, and then constant speed, which you announced at the beginning of the show. If you haven't caught the previous 3 shows, we've done a special on each one of these shows, or each one of these motor groups, technologies, so you can watch those webcasts and learn all about those motors. But the most common application of these motors is kind of interesting. I often get asked, well, how do you know that's a constant speed motor? Well, because it's in the outdoor application. Well, how do you know? It's just where the industry has landed that technology. The industry doesn't typically apply a constant speed ECM to an indoor blower motor. Conversely, the industry doesn't typically use a constant torque programmed motor as an outdoor fan motor. So you find constant torque and constant airflow in the indoor motors, and constant speed in the outdoor motors. And we're going to talk about that at the end. We'll kind of wrap back up with that. That has a lot to do with the air it's moving and the type of blade it's turning. So whether it's a forward curve fan or an outdoor fan, the programming, constant torque, speed, or airflow, some of those programming methods work better with different types of blades and under different types of loads. So that's a little teaser there for the end of the presentation. I also wanted to work in a little bit of history because I think, I don't know, maybe it's just me. I got older and I became a history nerd. I wasn't really a history nerd when I was a kid, but history became more interesting when I got older. But it's interesting if you watch this progression, and it's sort of interwoven in the presentation. It's sort of eye-opening where ECMs came into the industry and how much earlier they were around before most people thought they were in the industry.
Exactly.
So if we focus on the indoor blower motor side of the industry, and we talk about new equipment built, and we go all the way back to 1986, and you'll understand why I chose 1986. It's not just because I graduated that year, but we go all the way back to 1980s. Little giveaway there.
Hey, we got numbers.
You all the way back to 1986, and in the indoor blower application of new equipment, the number 1 motor used was a PSC direct drive motor. Now, I know there's somebody that's out there saying, oh, man, there were belt drives back then, and there were still some shaded yeah, there were some belt drives and some shaded poles, but the primary motor technology and HVAC equipment in 86 was a direct drive PSC motor. And it doesn't matter if it was a air handler, fossil fuel, package unit, that was the technology.
Right.
And the reason why I like to go back that far, there's a couple reasons why I like to go back that far. It helps understand the integration of ECM, but also because, we did 3 webinars on ECM motors, and we talked about PSC motors for probably a collective 5 minutes.
Yeah, not a whole lot about it. I mean, it wasn't
Nope,
the focus.
not a whole lot about it, but yet there's still the largest volume of motors used in residential HVAC today. And in tech support, I'm reminded every day how many contractors have not been taught as much about PSC motors as they have about ECM motors. So it's just going to take a little bit of time here, go back and talk about the PSC motors. PSC, again, stands for permanent split capacitor. It's an induction motor that uses an externally connected run capacitor to help with its starting and provides additional efficiency. You can identify it a couple of ways. You can physically see it, follow the wires out, and hey, what's that silver thing? That's the cap, and that's a PSC motor. Or you can look at the schematic on the motor. You got a little pictorial there showing you the cap, and you can see in the ratings where you've got the microfarad and voltage ratings of that capacitor. I'm sorry, every time PSC motors come up, I always have to say, if you're ever replacing a cap, make sure you replace it with the rating on the motor, not with the rating of the cap that was there before. Always check the rating on the motor. Sorry, little plug for proper.
Remember, this is all helping educators know how to relay this to the classroom. Yeah. This is all stuff that could be potentially missed. Yes.
Yeah. So if we switch to the outdoor fan motor, again, just talking about, I know we're in the indoor blower motor category in our history lesson, but we're in PSCs, so we'll talk about the outdoor fan motor PSC as well. Again, you can see the run capacitor out here. Most commonly in the outdoor unit, it's a dual run capacitor. So you've got a single common terminal with an F terminal for the fan motor and an H terminal for the compressor. I know H doesn't go with compressor, but it does if you know, hermetic, there you go. And then you can identify it by the diagram on the side of the motor as well. And again, the rating on the motor. So PSC motors, commonly built in 2 sizes, either 6-pole or 8-pole. And that's important because the blower wheels and fan blades that were used when PSC motors were king, and again, they were king up until just a couple of years ago. Fan blade and indoor blower wheel for PSC motors had to be designed at 25 RPM because those were your high-speed RPM values of 6-pole and 8-pole motors. And with PSC technology, and again, we're not going to drill all the way down to the amount of poles times the frequency, divided by 2. But the poles and the frequency determine the RPM. If you want a motor with a significantly different RPM, such as going from 1075 to 825, you have to get a completely different motor. You can't run a 1075 motor down at 800 RPM. I mean, you can, but it would be horribly inefficient and creating a lot of heat and probably wouldn't last that long. So that information will be very valuable when we progress into ECMs and understand the value of ECMs being programmable, but yet the fact that ECMs were used with the same blower wheels and fan blades that used to be used on the PSC motors and why they still operate around those typical 1075 and 825 RPMs, because the wheels didn't change, but the motor technology, the wheels and fan blades didn't change, but the motor technology did. So you've got indoor blower motors, typically multi-speed. They're multi-speed because quite often you've got a airflow requirement for the fossil fuel appliance that is different from the airflow requirement for the outdoor unit, whether it be AC or heat pump. And then you've got the outdoor fan motor, which is typically 1 speed because it's engineered by the manufacturer to run at the 1 speed necessary. Again, we're in 1986.
We're not into 2-stage yet.
Single stage equipment. Very good. Good catch there. So 1 speed. It's been engineered to operate at the 1 speed that maximizes the condenser TD across that coil, and that's what it does its whole life. So very simple motors. The average efficiency of a PSC motor is around 60 to 70%. They often get a bum rap. They're 60% efficient motors. Outdoor fan PSC motors can get up as high as 70% because they are optimized to run at the most energy efficient RPM range of a given motor with a given load in a given system. So when you pick the RPM point on the performance curve that is the most efficient, and you design your blower blade around that, then you can get quite a bit of efficiency out of a PSC motor.
Sure.
But when you're using multi-speed motors, the challenge with multi-speed motors is when you slow a PSC motor, any induction motor, down below its synchronous speed. So I said we wouldn't dig too far, but a 6-pole motor synchronous speed would be 1200. So any speed below that is moving away from its synchronous speed. The further you move away from synchronous speed by going to medium or low speed, the more inefficient the motor gets, the more heat it creates because the less mechanical energy it's creating. So multi-speed motors have these extra windings, and so we add resistance, more resistance, less amperage, less torque. So we've called these motors multi-speed motors forever, but technically they're multi-torque motors. As I reduce the amount of torque the motor can generate, blower wheel slows down and the speed changes. So going from the high speed to the medium speed, which is really going from the highest torque capability of the motor to the medium torque capability of the motor, I slow down in RPM, so we call them multi-speed motors. It's kind of tomato. It means the same thing, but I use this as the setup for the next motor or the second motor third motor we're going to talk about, which is constant torque motor, where we're going to start to understand that ECM motors absolutely focus on torque and speed, or just torque. They're not multi-speed motors at all. Why I go back to the PSC motor and say, well, they really never were. They're multi-torque motors that run slower when you go to a lower torque value.
I'm glad you represented it that way, because I actually haven't thought about that from that perspective. But 100%, when we change a resistance, we're changing the capable torque of the motor, consequently changes the RPMs of it.
Yep. Yeah, and another thing that is kind of interesting, since you gave me a pause there, you know when you're teaching, your brain's going a mile a minute, and sometimes you stop and you think of something else. When we get to the ECM, we're also going to understand how one motor can be more than 1 horsepower very easily by programming, and I don't need to build many different motors to do one thing. In other words, I can have one ECM that takes the place of 5 ratings of PSC motors because of a wider operational range and the fact that it's programmable. I can tell the motor what torque I want. I don't have to actually tap the winding. So on a PSC motor, let's say on this PSC motor, what I really wanted was I wanted a torque that was right about here, right? Yes. Well, I can't do that unless I'm gonna, do a YouTube special and open up a motor, break the windings open, and solder a wire in there. I can't get that torque value. It's been built, with the windings tapped here and here. But with an ECM, I can program it to give me that torque value or that torque value or that torque value. So I really open up the capability of a motor when I have programming versus tapped winding. And a tapped winding motor, it is what it is. It's never going to be anything else.
Okay. Great way to explain it. I'm sure there's a lot of teachers out here going, okay, all right, this makes sense. This is to deliver my content now.
There you go. That's what we're shooting for. The other thing that I think is kind of interesting, and this I can hear 5 or 6 people out there yelling, "That's not right." A PSC motor really only has a value in HVAC, in forward curve fan systems, and even in outdoor fan systems, only has a valuable operating range of about 200 to 300 RPM below its rating. So let's say you have a 1075 RPM motor. It's really only good to around 850, 900 RPM, somewhere in there. Because once you start slowing the motor down below, and you can operate it lower than that, but you operate it at an extremely inefficient place where it could be running less than 30% efficient. And it's going to be, because it's not generating as much mechanical energy at the shaft, it's going to be creating a lot of heat. So you're probably going to have a significantly reduced lifespan. So I'm not saying they can't operate below that range. They're valuable. Their long-term operational range and for efficiency and longevity is 200 to 300 RPMs less than what they're rated at. So there again, if I want one motor to operate from say 600 RPMs all the way up to 1200 RPMs, can't do it in PSC technology. I'd need 2 motors in a system. And interestingly enough, we went, me and another trainer at Regal Rexnord, we asked the engineers once, well, couldn't you build one? And just for fun, they actually did build one. They built a multi-pole motor, all in one motor. and it was half horsepower. So this is a half horsepower ECM. It was half horsepower, but it was this long because it literally had to have 2 sets of windings.
Separate winding.
Yeah. And it had like 16 wires coming out of it. It was really and truly the family truckster. It was nasty looking, but it was
into a replacement universal.
Right.
Work.
Yeah, but it was truly a 6 and 8 pole motor all in one casing.
Man, we have some fun. All right, everyone. I know it's been a long evening. I'm so grateful that you hung out with us. All of these presentations are available for you on YouTube, where you can go into our e-learning network at the HVACR Learning Network, and you can actually get credit for these courses if you're looking for that for continuing education. So check that out. We'll see you all at the conference. Everyone have a wonderful evening, and we will see you next week on Did You Know, the ESCO HVAC Show.
What a great time.